So last time I was previously talking about linear regression. That was the topic of 12.1. And I was talking about this so-called least squares line. We computed it using R, but I didn't actually explain what it was. So now I will define it precisely. Notationally, I'll write beta 0 for the intercept and beta 1 for the slope of this so-called least squares line, aka the line of best fit. So the question is, how do you define best fit? And how do you calculate beta 1 and beta 0? So here's a demonstration that someone programmed into Desmos. Let's see if this works, or GeoGebra. Okay, so you can see a few dots in this plot, and we would like to find a line that somehow fits them best. There's many lines you could draw, right? Lines of different slopes, lines of different intercepts. Does anyone know how we define best fit? Well, I'll tell you. Before I can define best fit, I first need to define these things called residuals. The residuals are the vertical errors. Let's see them. Boom, there. These little dotted line segments are the vertical errors. Now, you don't necessarily need to draw your errors vertically. Heck, you could draw them horizontally, perpendicularly, but in this class, and conventionally, the errors are drawn vertically, and the definition of the so-called least squares line is the line that minimizes their sum. The line that minimizes the sum of the squares of the residuals. So if I display squares for each of those residuals, we want the line of all possible lines that makes those blue square areas smallest. And it looks like it might be somewhere around here. Here, in fact, this demonstration will even calculate it for me. There, it turns out that that black dotted line among all possible lines is the one that minimizes the total blue square area. So let me reiterate everything I just said, because I was just saying it in words. So let me draw some pictures and equations. First, suppose that we have a scatter plot with some points. Let's say there's x1, y1. Maybe there's x2, y2. Maybe out here is xn, yn. Maybe right here is the ith point, x sub I, y sub I. And suppose that this is our line that we're trying to use to fit the data. So this is the line y equals beta 0 plus beta 1 x. Remember, we're using beta 0 for the intercept and beta 1 for the slope. The residuals are all these vertical errors. So, for example, right here would be my first residual, and we usually denote them with an epsilon. So this would be epsilon 1, the length of that segment. The length of the next segment would be epsilon 2. The length of this segment would be epsilon I, which apparently is the vertical distance between the point and the line. So that's the actual y value minus the predicted y value, beta 0 plus beta 1 x sub I. Here the epsilon n. Okay, so just to make sure you understand what these residuals are, suppose our data set consisted of the points 0, 0, 2, 3, 4, 3. Okay. Here's the point 0, 0. Here's the point 2, 3. Here's the point 4, 3. If we considered y equals 1 plus x over 2 to be our regression line, and I'm not saying that it is, but if it was, we could compute these three residuals. Let's see. 1 plus x over 2 goes through the point 0, 1, and then it's going to go up 1 and over 2. Up 1 and over 2. All right. So can you all tell me what epsilon 1 would be, what epsilon 2 would be, and what epsilon 3 would be for this line? So what's epsilon 1? That's the vertical distance between the line and the first point. First point was 0, 0, which is 1. So there's my epsilon 1. The vertical distance between the second point and the line is also 1, actually. Or actually, you know what? I guess technically epsilon 1 would be -1. Sorry. It actually doesn't matter whether it's negative because we're going to end up squaring it later. But just to be technically correct, it's -1, whereas epsilon 2 is +1, and epsilon 3 is, someone tell me what epsilon 3 is? 0. Okay. So, we want to find the line among all possible lines that minimizes the sum of the squares of these things. These are called residuals or errors. Those terms are used interchangeably. Computing the coefficients, that is beta 0 and beta 1, is a famous proof, or is a famous problem in analysis, calculus, and linear algebra. So again, we want to find the line that minimizes the sum of the squares of those errors. There's actually a name for this sum. There's two names for it. I apologize for the redundant notation, but both of these terms are used. So this line is this sum of squares is sometimes called the sum of squares of the errors, or the SSE, and it's also sometimes called the residual sum of squares. So both of those terms are used. How do you think you find the values of beta 0 and beta 1 that minimizes this sum? We're not going to do it, but strategically, how would you do it? This is a minimization problem for a function of two variables, right? You treat this expression as a function of two variables, beta 0 and beta 1, that you want to minimize, where the data, the x sub i's and y sub i's, are considered fixed. Has anyone taken multivariable calculus yet? In that class, you learn how to minimize functions of two variables. You take the partial derivatives with respect to them and set the equation to 0 and solve. So it turns out that solving this system of equations can be phrased or expressed as a problem in linear algebra. You end up with like a matrix system of equations, and there's a really cool linear algebra proof of the derivation of the solution. I've included the details of that proof in the notes, but we're not going to go over them. You're free to read it if you're interested. I'm just going to tell you the conclusion. The conclusion are two formulas for beta 0 and beta 1 that we will use. Beta 1 can be found to be this expression right here. So it's the sum of the product of the ith deviation of the x values and the ith deviation of the y values divided by the sum of the squares of the deviations of the x values. So that's how you get beta 1, the slope. Once you've found beta 1, you can plug it into this equation to get beta 0. So those are the two equations that we will use to get our slopes. There's other ways to express them, but these are the most useful and the simplest ways to express them. And you usually want to compute beta 1 first, and then plug that into the expression for beta 0 to get beta 0, right? Because the beta 0 expression has beta 1 in it. So let's practice. Let me now actually plug in values to those two equations and compute those coefficients for that same data set that we were just looking at in the previous example, 0, 0, 2, 3, 4, 3. And let's see what the true least squares line is. Because if this is our data set, then let's see, x bar, the mean of the x values, will be 1/3 of 0 plus 2 plus 4, which is 2. Y bar will be 1/3 of what? 0 plus 3 plus 3, which is also 2. Then the numerator of the expression for beta 1, the sum of the ith deviation of the x values times the ith deviation of the y values, will be, okay, so let's see, it'll be 0 minus 2 times 0 minus 2 plus 2 minus 2 times 3 minus 2 plus 4 minus 2 times 3 minus 2. So this is 4 plus 0 plus 2, which is 6. So I've computed the numerator of beta 1. The denominator of beta 1 is the sum of the squares of the deviations of the x values. So that's going to be, let's see, 0 minus 2 quantity squared plus 2 minus 2 quantity squared plus 4 minus 2 quantity squared, which is 4 plus 0 plus 4, which is 8. So beta 1 equals, I have now computed the numerator and the denominator. What's beta 1? Yes, very good. Because the numerator was 6 and the denominator was 8. So beta 1 is 6 over 8, or 3 over 4, or 0.75. Okay. I've got my slope. The other coefficient to compute is beta 0, so I'll use this equation. So beta 0 is let's see. Y bar was 2. X bar is beta 1 is 0.75. X bar is 2. So I get 2 minus 1.5, which is 0.5. So my least squares line, beta 0 plus beta 1x is 0.5 plus 0.75x. There. We just did a least squares line computation by hand. And in fact, you know what? Let's plot it. So my 3 points were 0, 0, 2, 3, and 4, 3. And let's plot this line. So let's see. There's 0.5, and it's going to go up 3 and over 4. Or up 0.75 and over 1. Right. Let's see, how can I do this? Up 0.5, which is the same. Hold on, that's the same as going up 1.5 and over 2. So it should go up 2 and over. Oh, so it should go through this point right here. Up 1.5 and over 2. There. Yeah, I think that's it. There we go. So there's y equals 0.5 plus 0.75x. Thus, we see that the minimum possible sum of squares for all possible lines is, let's see, the first residual is 0.5, or actually negative 0.5. The second one is positive 1. The third one is negative 0.5. So that would be 0.5 squared plus 1 squared plus 0.5 squared, which is what, 1.5, I believe. Is this smaller than the previous one? Let's just check. What was my residual sum of squares for the earlier line that I was using? This is really a test if you're following along with the notation and terminology. So I want to add up the sum of the squares of these 3 terms, giving me 2. So it is smaller. So that's good. All right. And indeed, you'll have to take my word for it that it's as small as it could ever be. There's no other line that will do better. Okay. And let me know if you have a question. Let's verify this in R, right? Because previously we were using the lm command. So let's make sure that the output of the lm command agrees with what we just did by hand. Where the heck is... Oh, there we go. All right, so let's let x be the vector of x coordinates, 0, 2, and 4, and y be the vector of y coordinates, which is 0, 3, and 3. Now, if I compute the linear model of y varying as x, I better get those same 2 coefficients, the 0.5 and the 0.75, and indeed we do. So we thus see how R computes the coefficients of a linear model. And there's the same line that we just computed and the same 3 points. So I would challenge you to find the least squares equation for this data set where we added a 4th point. I'm not going to do that now in the interests of time, but I would challenge you to come up with it by hand for this data set. to be clear, here's our notation so far. And I apologize because the notation is going to get kind of rough. Like there's going to be a bunch of different new definitions and terms. Our data set is denoted x1, y1 through xn, yn. The mean of the x values is, as usual, denoted x bar. The mean of the y values is, as usual, denoted y bar. Our regression line has intercept beta 0 and slope beta 1. We denote by epsilon sub I the ith residual. So again, I already drew this picture, but this is where if this is the line, beta 0 plus beta 1 x, and these are the points. Let's say this point is x sub I, y sub I, then this residual is epsilon sub I. And it's the difference of the observed and the predicted value. And the sum of the squares of the errors is, well, the sum of the squares of those residuals. And here are the two formulas for the coefficients that I just gave you. It becomes cumbersome to write this expression for beta 1 in totality. So I'm going to introduce yet more notation. You see the numerator of the beta 1 expression? We're going to call that S sub xy. It's the sum of the product of the deviations. Okay, so this numerator is now called S sub xy. And the denominator is the sum of the squares of the deviations in the x values. So we're going to call that S sub xx. And relatedly, by S sub yy, we mean the sum of the squares of the deviations of the y values. When I say deviation, I mean difference from the mean. And you'll see shortly why I make this definition as well. We haven't used this term yet, but we will. So in this notation, we could also express the formula for beta 1 as S sub xy over S sub xx. Okay, so let's practice with this. Suppose we would like to model the mileage of an electric car on the charge on its battery. Okay, so you collect a bunch of electric cars, you charge their batteries, you drive them until they run out of juice, and you observe how far they were able to go so that you can predict how the charge on the battery affects or predicts the mileage. That's how far the car can go. Now, obviously, there's going to be differences in electric cars, differences in road conditions, weather conditions, traffic conditions. So you're not always going to get results that lie on a straight line. There's not exactly a linear relationship. There's all sorts of other variables. So suppose these are the 10 kilowatt hours charged to these 10 vehicles. And these are the respective miles that the vehicles were able to travel. Let's compute the regression line and answer a few questions. So let's let x. Oh, by the way, so what would I be treating as the independent variable here? Are we modeling mileage off charge, or are we trying to predict the charge from the mileage? Yeah, the charge is what you can control. So that's our x variable. That's the independent one. So let's let x be the vector of charges, and let's let y be the vector of respective mileages. Okay. With that, I'm going to compute beta 0 and beta 1. And I'm going to do it using vector arithmetic in R, and then I'll verify my answer using the linear model command. So let's see. I'll need the what I called S sub xy, capital S sub xy. That was the sum of, oh, here, let me let x bar be the mean of the x's, and let me let y bar be the mean of the y's, then then the sum of the product of the deviations, of the ith deviations in the x's and the y's would be the sum of the product of x minus x bar and y minus y bar and I'll also need S sub xx, which is the sum of the square of the deviations in the x values. So that's x minus x bar. So if I did this right, beta 1 should be sxy over sxx. So supposedly, beta 1 is 3.635. And beta 0 is, according to this formula here, y bar minus beta 1 times x bar. This is going to be y bar minus beta 1 times x bar. Okay. So let's see if I did this correctly. See if the linear model command gives me the same thing. Hope I get 3.635 and -73. Whew. Okay, good. You're good. I didn't screw it up. So, now you see how you could do these computations by hand and verify them with the linear model command in R. And if we plot this line on top of the data, we get a plot that looks like this. So let's see if we can interpret it now. What's the interpretation? Remember that I told you last time how to interpret the slope and the intercept and and the regression line. Remember, like, regression line gives predicted average response, the predicted average y value for a given x value. The slope gives you predicted change for a 1 unit change in x, and the intercept gives the prediction for when x is 0, if it's even in the scope of the model. So in this case, can someone interpret the slope for me? What's the interpretation of the slope? Which was this. So this is what? Yes. Yeah. So for every additional kilowatt hour of charge on the battery, the car can go an additional 3.635 miles. Or, yeah, I think it was miles, right? Yeah, miles. So in fact, this is you know how when you buy a car, you typically want to check how many miles per gallon it gets. This is like the miles per kilowatt hour that it gets. So this is a very important number that you would want to know if you were thinking about buying an electric car. So comparable to miles per gallon for gas vehicles. All right. Can someone interpret the y-intercept? What's the interpretation of this number? Yes. Yes. Good. Very good. Very good. So in theory, this would be the predicted mileage for a car with zero charge, but clearly a negative mileage makes no sense. What, like you don't plug your car in at all and you can still go 73 miles backward? Yeah, that's obviously nonsense. So this is outside the scope of the model, as you can infer from the fact that we have no x values near zero. And if we did, well, let me not say that. Yeah, so I think here, where is it? Yeah, here. This value of -773, -73, is clearly beyond the scope of the model. And if you plot the line at zero, it kind of looks like you need at least some positive amount of charge to even get the car moving. Maybe to, I don't know, overcome the force of static friction or something. So this is beyond the scope of the model. All right. What if you wanted to know how much explanatory power your model had? So as you can see, the data does not lie perfectly on a straight line. So you can't predict the mileage exactly from the charge on the battery. There's still variation in randomness due to other sources, differences in makes and models and road conditions, weather, etc. So how much explanatory power does our model have? It turns out that we can quantify this. So I introduced about 10 minutes ago the notation S sub YY for the sum of the squares of the deviations in the Y values. We also call that, and again, I apologize for the redundant notation, the sum of squares total, or SST. So that's the sum of the squares of the deviations in the Y values. I also defined already today the sum of the squares of the errors. So let's see if I can explain this. This expression SST gives the total variation in the y values. This expression, SSE, gives the variation in the errors, that is, the deviations about the predicted values. Question: if the model is really good, do we expect this to be large or small? The sum of the squares, the errors. Right, yes, errors are bad. These are deviations from the predictions. So when the model is good, the errors are small. And the ratio of the sum of the squares of the errors to the total variation in y is then the variance in the y values left unexplained by the model. Again, this is kind of a mouthful, kind of a tricky concept. The ratio of SSE over SST gives the percent of the variation in y which is not explained by the model. That is not simply due to x. So if I take 1 minus that expression, I get the variation in y which is explained by x. So this quantity, which is a percent, a number between 0 and 1, is the explanatory power of the model. It's how much of the variation in y is explained by x. And we give a name to it. We call it the R-squared statistic. The book calls it the coefficient of determination. I don't like that name, and I don't think it's very common. I think R-squared is the more common name. And it's possible to prove, by the way, that you can express it as S sub xy squared over S sub xx times S sub yy. You don't need to prove that or know the proof. You can just take my word for it. But we have a notation for the R-squared statistic. Guess what our notation for R-squared is? You're never going to believe this. Yeah, we use an R squared. Okay, so we will denote the R-squared statistic by an R with a square. And we'll either use a capital R or a lowercase r. And in about 10 minutes, you'll see why we call it that. So let's see what proportion of the variance in mileages is explained by the variation in charges. So I'm going to need what S sub yy. So S sub yy, that would be the sum of the squares of the deviations in the y values. And then if I do, let's see, I can use either the formula on the left side or the right side of this equation. I'll just use the right side. I think that's a bit easier. So using this expression for the R-squared statistic, let's see what we get. S sub xy squared divided by S sub xx times S sub yy. Okay, so we get out 0.911. Oh, and I need this one. All right. Thus, we see that about 91.1% of the variation in mileages is explained by the amount of charge that was on the electric vehicle battery. So any questions? You can also compute this in R, by the way. If you summarize the linear model command, it turns out that it will output this thing called multiple R squared. And indeed, we get the same value. So FYI, there's a whole bunch of other output of this summary that we aren't going to have time to cover, unfortunately. Like, it turns out you can do inference on beta 0 and beta 1. That's kind of neat. Think about that philosophically. There exists some true linear relationship between a pair of variables. You don't know what it is. You collect sample data. There's variation in your sample data. You can use that random sample data to, for example, come up with a confidence interval for what you think the true slope of the regression line is, right? God knows what the coefficients of the regression line that relate, I don't know, say mileage to charge or height to weight, or you name two variables that have some true but unknown linear relationship. So anyway, we're not going to have time to cover it in this class, but in the textbook, you can read about performing inference on the regression coefficients. Okay, cool. I'm doing all right. Let's keep talking about this R squared statistic. And first, I need to detour slightly to something called correlation. You've all heard the word correlation. It's an English word. It also has a precise meaning in statistics. It's a measurement of the strength of a linear relationship. And we'll denote it by R. So R is sometimes called the correlation coefficient, or the R statistic, or the correlation, or sometimes Pearson's R statistic, I think, is another name used for it. And it's defined to be capital S sub xy over the square root of capital S sub xx times capital S sub yy. So here's or equivalently, this complicated fraction here. So it looks kind of brutal to compute. We could do it, but obviously you would typically use software to do it. I don't know if I've ever computed one by hand. I've probably computed one or two by hand, but you would almost always use software. And the R code for computing the correlation R is core, C-O-R, and core of the vector of x data and the vector of y data. Here's a bunch of facts about the correlation coefficient. It's only meaningful for linear relationships. It's always between -1 and +1, inclusive. The sign of R matches the slope of the regression line. So if there's a positive relationship, then R is positive. If there's a negative relationship, then R is negative. The closer it is to either +1 or -1, however, the stronger the relationship. If R is exactly +1, that means your data lies exactly on a line, a line with positive slope. R is pretty cool, by the way. It has all these interesting properties. Another useful, interesting property is that it's unitless. The fact that it's unitless, well, okay, hold on. I'll get back to that. Here's another cool property. It doesn't depend on which vector you input first. So the correlation between x and y is the same as the correlation between y and x, right? You can flip the order of the arguments. You can even linearly transform one of the vectors, and that won't affect the correlation. So if I scale one of my data sets by a constant and add a constant, the correlation is unaffected, at least if the scalar is positive. So for example, let's say X was a bunch of temperatures in Fahrenheit, degrees Fahrenheit, and Y was a bunch of, I don't know, what's something that probably depends on temperature? I don't know, like hours of sunlight or joules of energy let off by some engine, or I don't know, like, let's just say, uh, joules of energy that were produced by some engine. The point is, if I correlate these two data sets, if I compute the correlation between these two data sets, how will it be affected if I had used Celsius instead of Fahrenheit? Yeah, it would not be affected. So you can change your units and the correlation's unaffected. All right, so that's really useful. R is unitless. It doesn't depend on the units of your data. And it's related to the slope of the regression line beta 1 via the following equation. It turns out that beta 1 is R times the standard deviation in the Y values over the standard deviation in the X values, which can also be expressed as R times the square root over the sum of the squared deviations in the Y values divided by the square root of the sum of the squared deviations in the X values. Again, I apologize for the notation here. So here I'm using lowercase x sub s sub x and lowercase s sub y. These are the familiar sample standard deviations that we learned about at the very beginning of this course. Don't confuse them. They aren't quite the same as capital S sub x x. They're related, but they're not quite the same. And here's how I remember this equation. So if you look at the regression line, y equals beta 0 plus beta 1 x, beta 1 is the slope. So has units of y over x. Just remember that. Beta 1 has units of y over x. So hence, and R is unitless. So beta 1 has units of y over x. R is unitless. The way I can remember this equation is that I need this factor to also have units of y over x. So that's how I'm able to remember the fact that s sub y goes on top and s sub x goes on the bottom. I know there's a lot of equations. By the way, if you have a copy of the final exam formula sheet handy, it's good to maybe keep an eye on that to be able to keep track of all these equations. All these equations are on the final exam formula sheet. Let's take a look at some scatter plots and their various correlations. So here's one with not much of a correlation. It's about 0.4. Here's a strong positive correlation of +1 and a strong negative. This is what a correlation of 0.93 looks like, and a slightly weaker negative one. What does the correlation say about this scatter plot, or this relation? Like, look at this parabolic relation. Is there a strong relation here? Yes, clearly. But is it linear? No. So correlation is not meaningful for such a relationship. Similarly, in a relationship such as this, correlation is not meaningful. So for any of these that are nonlinear, don't even try to read into it. It's not appropriate to compute the correlation. You would first want to, for example, do some sort of transformation to make it a linear relationship, and then you can try to make sense of the correlation. Yeah. Looks like I included all the code that I used to generate all of these. So I think we can do a fun little game now where I'm going to give you all practice with guessing the correlation. All right, so let's go to guessthecorrelation.com. And first I'll do it, and then I'll see how good you are. Ah, crap. Of course, does this stupid thing. All right. So let's see that. No, that looks like a pretty weak one. I'm gonna say that's like 0.25. Oh, already lost. You get a few guesses. Or here, all right. Someone else want to guess? All right, Luke, what do you think that one is? You have to get it within 10%. I think it's higher than that. All right. We're going off. It was 0.36. Good job. All right. So it was a Gabe or Joe? Sorry? Oh yeah, Adam, sorry. Yeah, all right. Adam, we think this one is. All right. 3%. All right. Skylar, what's this one look like? That's it. All right. 0.04. That's 29%. Man. All right. Blake, what's that one? Yeah, that's pretty strong. Okay. Ooh, nice, man. All right. All right. I guess you get to go again. What's that one? 7.5. Wow. You're on a roll. All right. What's that one? 9. Wow. 3 in a row. Cool. Okay. Let's see. So yeah, that was a streak. All right, here. Let's get you all involved. Natalia, want to do this one? 0.2. Okay. Wow, you're good. Okay. And Abby, what's that one? Oh, you were as far as you could be without losing a point. So we were close, but one more percentage point off, and you wouldn't have gotten credit. Okay, cool. All right. So yeah, that's correlation. Just giving you all a feel for being able to sort of eyeball correlations. Now let's relate this back to the R squared statistic that I defined like 10 minutes ago. So it turns out that the R squared stat is just the square of the correlation, right? So that's why we use that notation. That's why we denote the correlation by R and the R squared statistic by, well, R with the square, because it is in fact the square of the correlation. So for example, here, let's, yeah, here, let me just verify these equations for the miles per kilowatt hour example. So I said that, let's see, R was, what was it? It was S sub xy over the square root of S sub xx times S sub yy. Yeah. Which turns out to be 0.954. That should be the same thing that I get if I plug x and y into the correlation command. And indeed, I get the same thing via COR. And if I square this, I should get the R squared statistic that I found previously, which was 91.1%. And there it is. Okay. Let's see. Should we do a unit question? So suppose we converted our kilowatt hours to watt hours in that miles per kilowatt hour example. how would the slope change? Slope of the regression line change? And how would the correlation change? So can someone tell me how the slope of the regression line would change? So the original slope was 3.635, and that was in miles per kilowatt hour. Torp? Sorry? Let's see. So I want to convert kilowatt hours to watt hours. Yeah. Oh, good. Yes, which does mean divided by 1,000. Cool. Yeah. So the new slope would be 0.00365 miles per watt hour. That's how the slope of the regression line would change. So we would do the same thing to the correlation now. Yeah. How would the correlation change? It wouldn't change. The correlation would remain the same. Yes. Okay. There's a pretty cool consequence of the equations of the regression line that explains how it got its name. Like, where, I don't know if this thought occurred to anyone, but did you ever wonder why we call it a regression line? What, like the name least squares makes sense. The name line of best fit makes sense. Why do we call it a regression line? Well, it turns out to be a consequence of an equation that I gave you previously, which is this equation. So remember, beta 1 is the change in y predicted by some change in x. Or I should say the change in y predicted by a 1 unit change in x, or the ratio of delta y over delta x. Well, it's possible to prove that correlation is always less than or equal to 1. And if you take that equation, delta y over 1 equals beta 1 equals r times s sub y over s sub x, and you use the fact that r is less than or equal to 1, we can see that the change in y that corresponds, let's see, how should I say this? I'm trying not to go into too much detail here and just give you the punchline in the interests of time. So here's the punchline. A 1 standard deviation change in x predicts less than a 1 standard deviation change in y. At most, if you deviate x by a standard deviation, it will also deviate y by a standard deviation. And that's for the case that the data lies perfectly on a straight line. And that's almost rarely the case. With almost any real world data set, you're going to have some variation around the regression line. It's not going to be a perfect line. So if you deviate 1 standard deviation from the mean in the x values, that will predict a deviation in the y values, but not by as much. In other words, the y values regressed to the mean on average. This is why. So as a consequence of this fact, tall parents have tall children who are, on average, not as tall as the